In this continuation of our introductory videos, I'm going to talk about set operations. First of all, if A and B are two sets, then the union of A and B is defined to be the set of all x which are in A or B. A lot of you are probably familiar with what are called Venn diagrams, which are just graphical ways of representing certain set operations. The Venn diagram that represents the union of two sets is shown here. If A and B are two sets, then the union is just everything that's in A or B. Venn diagrams are useful for trying to get some intuition about what's going on in certain mathematical proofs. But as a word of warning, just drawing a Venn diagram is not usually considered a rigorous form of mathematical proof. A Venn diagram can be useful for illustrating why some mathematical statement is true. But when you want to rigorously prove it, it's better to try to write out the argument using sets and logic notation. I think a lot of you are probably familiar with this basic stuff, and so I'm going to go through it rather quickly. The intersection of two sets A and B is just the set of everything which is in both of the sets. In other words, it's the set of x which are in A and in B. To give a simple example, just to make sure we're all speaking the same language, consider the set A consisting of the letters A, F, and I, and the set B consisting of the letters A, B, F, and G. The union of these two sets is the set of all elements which are in A or B, or possibly both. In other words, it's what you get by putting all of the elements of A together with all of the elements of B. Since these are sets, we're not allowing repeated elements, so A union B is just going to be the set consisting of the letters A, B, F, G, and I. Similarly, the intersection of these two sets is going to be the set of all elements which are in both of the sets. By examination in this case, we can see that A intersect B is the set consisting of the letters A and F, since those are the only two letters that both sets have in common. Now, there are some basic properties of unions and intersections which follow directly from the definitions. I've listed some of the main ones here, and I've divided them into three categories. First of all, there are the commutative properties, which say that if you take a union or an intersection of two sets, it doesn't matter what order you write the two sets in. So A union B is the same as B union A, and A intersect B is the same as B intersect A. Then there are the associative properties, which say that when you're taking a union of three sets or an intersection of three sets, it doesn't matter what two sets you decide to consider first. In other words, it doesn't matter how you put the parentheses on these sets, you will get the same answer. And finally, there are the distributive properties, which need a little bit more thought, but which are also easy to show. The distributive properties combine unions and intersections in two different ways. The first distributive property here says that if you take A union B and then you intersect that with a set C, you will get the same thing as if you intersect A with C and B with C and then take the union of those two sets. In the second distributive property, the roles of the union and intersection are interchanged. If you take the intersection of two sets A and B and then you union that with a set C, you'll get the same answer as if you form the union of A and C and intersect that with the union of B and C. These are basic but important properties of the union and intersection. But in practice, they're also pretty intuitive, so you probably don't need to try to make an extra effort to memorize them. It's also important to define unions and intersections of arbitrary collections of sets. In order to do that, let's suppose that we have some indexing set capital I with labels little I that we use to label some collection of sets, A sub little I. The notation curly braces A sub little I with little I running through capital I means the collection of sets A sub little I where little I runs through the indexing set. When you have a collection of sets like this, the union of the collection of sets, which is denoted as you see here, is defined to be the set of all x's which are in at least one of the sets A sub little I. In other words, it's defined to be the set of x's with the property that there exists a little I in big I, such that x is an element of A sub little I. This is a straightforward generalization of our definition of unions of two sets. Similarly, the definition of the intersection of the collection of sets A sub little I is as follows. The intersection, little I running through big I of the sets A sub little I is defined to be the set of all x's with the property that, for every little I in big I, x is an element of the set A sub little I. In other words, the intersection of the collection of sets is the set of all x's which are in all of the sets A sub little I. Now, this can be a little tricky for some people, so I want to take a look at an example. In the example, I'm going to let my indexing set be the set of natural numbers. So I'm going to define a collection of sets A sub little I, where I runs through the set of natural numbers. I'll define the first set to be the set consisting of the numbers 0 and 1. Then I'll define the second set to be the set consisting of the numbers 0, 1, and 2, and the third set 0, 1, 2, and 3, and so on. In other words, for every little I in the set of natural numbers, I'll define a set a sub little I to be the set consisting of the numbers 0, 1, 2, and so on up to the integer little I. Now, it's not difficult in this example to see that the union of the collection of sets a sub little I is precisely the collection of non-negative integers, and that the intersection of this collection of sets is simply the set consisting of the integers 0 and 1. Even though this is a relatively easy example, I'd like to show you how to formally prove these facts, if nothing else just to get some practice writing proofs using this kind of language. First of all, how do we prove that the union of the collection of sets AI is the set of non-negative integers? Well, remember from a previous video that to prove that two sets are equal is equivalent to showing that one set is a subset of the other and vice versa. So what we want to do here is we want to use the definition of the union to show that the set on the right is a subset of the set on the left, and that the set on the left is a subset of the set on the right. First of all, for one direction of the proof, let's suppose that I have an element n of the set of non-negative integers. Well then, by construction, n is going to be an element of the set an. So by the definition of the union, n is going to be an element of the union over little I and I of the sets ai. Since every element of the set on the right is an element of the set on the left, that shows that the set on the right is a subset of the set on the left. For the other direction, let's suppose that m is an element of the union of the AIs. Well, the fact that m is an element of the union means, by the definition of union, that there exists an I in I such that m is an element of the set a sub I. Since every one of these sets a sub I is a subset of the set of non-negative integers, that guarantees that m is actually a non-negative integer. And that gives us the other inclusion, that the union of the AIs is a subset of the set of non-negative integers. That establishes the first fact that the union of the AIs is equal to the set of non-negative integers. We can prove our claim about the intersection of these sets being the set 0, 1 in a similar way. First, suppose that n is an element of the set on the right-hand side. Well then, n is 0 or 1, and so whichever one it is, by the construction of the AIs, it's going to be an element of the AIs for all little i's in I. Well then, by the definition of intersection, that qualifies n to be an element of the intersection of the AIs. And that gives us one inclusion, that the set containing 0 and 1 is a subset of the intersection of the AIs. To prove the other inclusion, let's suppose that m is an element of the intersection of the AIs. Then, by the definition of intersection, m has to be in all of the sets a sub little I. So in particular, m has to be an element of the set a sub 1. But the set a sub 1 is just the set consisting of the numbers 0 and 1. So this shows that the intersection of the AIs is a subset of the set consisting of 0 and 1. Since we proved both inclusions, that proves that these sets are actually equal to one another. Moving on, we have a couple of basic definitions. First of all, we say that two sets A and B are disjoint if their intersection is the empty set. And similarly, if we have a collection of sets, a sub little I, indexed by some indexing set big I, we say that the collection of sets is pairwise disjoint if the intersection of a sub I with a sub j is the empty set for all pairs of indices I and j with I not equal to j. These are basic but important definitions that we're going to use later on. Our next set operation is the set difference operation. If A and B are two sets, then the set difference of A minus B, which is usually denoted by A backslash B or A minus B, is just the set of all elements of A which are not elements of B. So for example, using the two sets A and B from before, we have that A set minus B is just the set containing I, and that B set minus A is the set containing B and G. One important point to note from this example is that the set difference operation is not necessarily commutative. In other words, it's not true for all sets A and B that A minus B is equal to B minus A. Now, there are some examples of sets A and B for which this is true, and I'll leave it to you to figure out exactly when this holds. But just remember that it's not true in general. Related to this is what's called the symmetric difference operator. The symmetric difference of two sets A and B is the union of A set minus B and B set minus A. In other words, it's the union of all of the elements of A which are not in B with all of the elements of B which are not in A. The usual notation for this is A triangle B. For our sets A and B from before, we already computed the set differences of A minus B and B minus A, so the symmetric difference is just the union of those two sets. And it's also clear from the definition, together with the commutativity of the union operation, that the symmetric difference is also a commutative operation. In other words, for any sets A and B, A triangle B is the same as B triangle A. Our next set operation is the complement operation. If A is a subset of a set X, then the complement of A in X is the set of everything in X that's not in A. Equivalently, it's X set minus A. And the notation for this is to write A superscript C. You have to be careful about this because even though the notation doesn't depend on X, the definition of the complement of A in X does depend on X. I'll give you a simple example in just a minute to show you what I mean. The second important property, which is not difficult to prove, is that if you take the complement in X of the complement of a set A in X, you recover the original set. It's kind of easy to see why this should be true from the Venn diagram, and it's also not difficult to prove it rigorously using the definition. Okay, now let me give you an example to make sure that you understand my comment from before. The natural numbers are a subset of the set of integers. So if I'm thinking about the set of integers as the universal set that the set of natural numbers lives inside of, then I would say that the complement of A in X is just the set of non-positive integers. On the other hand, if I'm thinking about the universal set in which the natural numbers live as being the set of rational numbers, then the complement of A in X would be the set of all rational numbers which are not natural numbers. Of course, the second set includes the first set as a subset, but it's a proper subset. The two sets are definitely not equal, because the second set, for example, contains the number 1/2, but the first set doesn't. This is just something to keep in mind when you're working with complements of sets that could naturally be thought of as subsets of different universal sets X. Now I want to talk about a very important set operation called the Cartesian product. Given two sets A and B, the Cartesian product of A and B, denoted by A times B, is the set of all ordered pairs of the form parentheses A comma B with little a in A and little b in B. These ordered pairs are just new objects built from the elements of A and B, and the rule is that two ordered pairs are equal to each other if and only if their A coordinates are equal and their B coordinates are equal. To give a couple of simple examples, first let's let A be the finite set consisting of the numbers 1 and 2 and the letter X, and let's let B be the set consisting of the numbers 1 and 2 and the letter Y. In this case, because both sets are finite, we can list out all of the elements of the Cartesian product A times B. We just go through and think about all of the ways of creating an object of the form parentheses, element of A, comma, element of B. This is a pretty easy example, but one thing just to pay attention to here is that 1, 2, and 2, 1 are not the same as ordered pairs. That's the reason why they're called ordered pairs, because even if A and B happen to have some of the same elements, the order that you list different elements when you're constructing an ordered pair does make a difference. Another example which I think we're all familiar with is the Cartesian product of R with itself, which is just the set of all ordered pairs of the form xy, where x and y are real numbers. A lot of times we just call this R2, and in this case we have a nice geometric description which allows us to visualize the Cartesian product. We can think about points xy as being x, y coordinates in the Cartesian plane. In general, sets and Cartesian products of sets may not have such a nice geometric description, but when they do, we often use it to our advantage to try to understand them. It's pretty straightforward to extend this definition to define the Cartesian product of a finite collection of sets. If A1 out to AN are sets, then the Cartesian product of A1 to AN is defined to be the collection of all ordered n tuples, little a1 out to little an, where each of the little ai's comes from the corresponding set AI. There's also a way of defining the Cartesian product of an arbitrary collection of sets, in other words, even an infinite collection of sets, and we'll talk about that in the next video about functions. A special case of this definition is when all of the sets are equal to some set A, and in that case we often denote the Cartesian product of n copies of A by a to the n, and we refer to this set as the collection of ordered n tuples of elements of A. Just to say a couple more words about this, first of all, it's pretty easy to show that if you have n sets which are all finite, then the cardinality of the Cartesian product of the n sets is the product of the cardinalities of the sets. That's just because the number of ways of choosing an element from the set A1 is the cardinality of A1, the number of ways of choosing an element from the set A2 is the cardinality of A2, and so on. And when you're building an ordered n-tuple from these sets, making a different choice at any position in the n-tuple will result in a different element of the Cartesian product. Now, I also want to mention one thing, just in the way of warning, and that is that the symbol that we use for Cartesian product is also used for other things in this subject. For example, later on, we're going to use the same symbol to define direct products of groups. You should be aware of this when you're writing proofs, and also when you're reading mathematical texts, because sometimes the time symbol can carry more information than just denoting a Cartesian product of sets. The final set operation that I want to talk about is the power set of a set. The power set of a set A is the set of all subsets of A. Pay attention to the fact that the elements of the power set are themselves sets. So this is a set of sets. It's the set of all subsets of A. Two common notations for the power set are to write curly P of A or to write 2 to the power A. I usually prefer to use the first notation, but you'll see the reason for the second notation in just a minute. This is an important set operation, so let's look at a few examples. First of all, let's consider probably the simplest example, which is when the set A is the empty set. Does the empty set have any subsets? Well, I hope that you answered yes, because of course any set has a subset. The empty set is always a subset of any set, and the set itself is also a subset of the set. Now in this case, the set itself is the empty set, and so the only subset of A is the empty set. That means that the power set of A is the set whose only element is the empty set. For the second example, let's consider a set A consisting of one element, and let's suppose that that element is a triangle. To list out the subsets of this set, I can just go in order of increasing cardinality of subsets. So first of all, I have the empty set, and then I have the singleton set consisting only of a triangle, and then since A only has one element in it, I'm done. So the power set of A in this example is the set whose elements are the empty set and the set containing a triangle. What about if I start with a set that has cardinality 2? Here A is the set whose elements are the number 1 and the set containing the number 2. I list out the subsets of A. There's the empty set, the two singleton sets, and then A itself, and then I'm done. Notice that in the first example, I started with a set that had cardinality 0, and the power set turned out to have cardinality 1. In the second example, I started out with a set that had cardinality 1, and the power set turned out to have cardinality 2. And in the third example, I started with a set that had cardinality 2, and the power set turned out to have cardinality 4. If this is not enough data points to be able to understand the pattern, then you can work out for yourself that the cardinality of the power set of a set with 3 elements turns out to be 8. After you've done enough examples, you will probably convince yourself that if the cardinality of A is n, then the cardinality of the power set of A is 2 to the n. This is also the reason why some people use the notation 2 to the A to denote the power set of A. Now, I want to conclude by explaining in 2 sentences why this is true. Let's suppose that we have a set A with finite cardinality n. In order to pick a subset of A, you can just go through the elements of A one by one and decide whether or not to include them in your subset. Making a different choice for any one of the elements of A is going to result in a different subset. So the first sentence in the proof is that every possible subset of A is uniquely determined by looking at each element of A and choosing whether or not to include it in the subset. The second sentence is that there are 2 choices for each of the n elements. So the total number of subsets is 2 times 2 times 2, n times, which is 2 to the n. And that's the end of the proof. Some of you may have seen longer proofs of this in your classes or in your textbooks. And the reason why is that actually this proof is hiding the fact that we're relying on the principle of mathematical induction. So maybe technically I should put quotes around the word proof here. But at the very least, this gives you one way of easily understanding why the theorem is true. That's the end of this video. There are only 2 more preparatory videos before we start talking about groups. And in the next video, I'm going to talk about basic definitions and properties of functions.